Welcome back to More Organic Chemistry. Hey, today we're changing gears. Most of the time we talk on these videos about reactions and mechanisms and memorizing reagents. Okay, we're going to make a big shift. Today we're talking about how to determine the structure of an unknown compound. Turns out we're going to need several pieces of information. And so we're going to talk about one piece of information today, and that is mass spectroscopy. Okay, so this begins key concept, unit 4, part 1. And the whole topic, pen please, there it is all about structure elucidation or structure determination. So that's our goal for unit 4. If you want more background information, if you want to Google something, structure determination works, although I think you'll get more hits with structure elucidation. That's a more common term for doing this type of analysis. And it's kind of cool. I know some students have mixed feelings about it. Some students are like, yay, I don't have to memorize mechanisms in unit 4. And okay, yeah, whatever motivates you, right? Others are like, oh, this is challenging because I don't get to memorize stuff. Like, you have to figure it out. But take a positive view. Think of it like a puzzle. It's a puzzle. We want to solve this. And I give you partial credit. Showing your work goes a long ways. And if you practice, you can get better at it. So, and it's kind of fun. Anyways, hopefully that motivates you to do well in this unit. Okay, so what's this unit about? So first thing we're going to talk about is mass spectroscopy, mass spectrometry. It's all about trying to measure weights of molecules. And from that, we can figure out what their chemical formulas might be. And that gives us a lot of information as to what the molecule might actually look like, how it's put together. So mass spectrometer, I got some fun pictures over here. Back in the 60s, that's what they look like. And now they look like this. And it turns out, I don't know if you stare a little bit, these are little vials here. This is an auto sampler where you load up the compounds you want to analyze in these little vials. This has an injector, puts it into this instrument right here. This is actually a gas chromatograph, a GC. So it separates the molecules and then one by one inputs different molecules through this little transfer line here into the mass spectrometer. There's the mass spectrometer over here. And so there's a very common instrument called a GC mass spec, GCMS, where you take your mixture and analyzes it, gets you lots and lots of information about multiple compounds. Cool stuff. All right, there's another video that kind of goes into the background of mass spectrometers and how they work. Take a look at that. There's lots of different ways the procedure's done, but it all comes down to 3 points. First point is you gotta get those molecules into the gas phase, and you have to give them charge. You have to make them ions. Once they're ions, you can use magnetic fields and other methods to figure out their mass to charge ratio. And that's the key. This is pretty cool. We're actually measuring the mass to charge ratio for individual molecules. Molecules you can't even see. They're too tiny. But these instruments are quite powerful. Had them since the 60s. And the key is if you get them charged, they can interact with a magnetic field and we can sort them or distribute them and somehow get their mass to charge ratio. M to Z ratio, it's called. And then inside the mass spectrometer, right, you're doing all these steps. First, you're getting the molecules in the gas phase. That way you have individual molecules. In the liquid phase, they're all stuck together. Solid phase, they're stuck together. I get them in the gas phase so they're separate. Give them charge. Charge allows us to separate them on the basis of mass to charge ratios. And then finally, you have to detect them. And because they're charged, you usually get an electric pulse, use electronics to count, actually detect them and count them. Count their mass, but also count the numbers of molecules coming into the device. Cool. Okay, so just real quickly, here's a quick overview. Again, look at the other video for more information. But in one typical setup, you have a probe that's going to inject individual molecules in the gas phase. We got this coil of wire over here that's heated, emitting electrons. Electrons fly across here and collide with the molecules. Our molecules are trying to figure out the unknown. It's like, what are these molecules? Well, they're in the gas phase, bombard them with electrons, knock out an electron out of their molecule. So then they have a positive charge. And then we put some voltages on these little metal plates inside here. This is a tube. These are little slits in the metal plate. And but based on the charge, we can shoot these through here and accelerate the ions, the molecules that now have charge, and they can interact with the magnetic field. And that's the key. If they have charge, charges in motion interact with the magnetic field and they get bent, well, there's a torque put on them, the physicists would say. And the key is if they're too heavy, it's like a big old Mack truck taking a turn too fast, it's going to fly off the side of the road. It's going to collide. If it's too light, it might turn too sharply. It will turn too sharply and collide with the inside track. Only mass of the exact right amount, right speed, right mass, right charge can actually navigate that turn perfectly. And then there's more slits here to make sure that some aren't just off center. And by knocking those, collecting those with a slit here, you sort out individual molecules that have exactly the mass and velocity and charge, and then you detect them. And what you can do is you can use an electromagnet, change the strength of the magnetic field. You can change the voltages on these plates, change their charge, change their velocity as the ions come out and they're being repelled or attracted by these plates. You can adjust this with electronics, fine-tune the electronics, so then you can get this heavier ion, increase the magnetic field so it can bend it more, so the heavier ion can actually navigate through and detect it. And then knowing your settings here and you calibrate the instrument, you can actually detect them and measure their masses. Quick little overview. Look at the other video for more information. This video is going to show us how to take the data and from that try and get some possible chemical structures, right? Structure elucidation. What's the molecule look like? Okay, key things that you need to know so that you can interpret the data, so that you can do a good analysis. First thing you need to know is that most commonly you only remove one electron. So that's our assumption. We're going to remove one electron, and that makes the molecule technically a cation or radical. More on that in a minute. But back to the one electron being removed. Well, to our mass to charge ratio, then we have an m to z value of m over +1, which reduces the mass. So the physicist says we're not measuring mass, and then that person's right. But if we make the assumption, which is generally valid, that only one electron is being removed, then the mass to charge ratio reduces to mass divided by 1, which is the mass. And so we are measuring the mass directly. Cool. Key point 2, go back to the instrument we just explained, and we talked about individual molecules flying through here. So what mass are we measuring? We're measuring the mass of individual molecules, individual atoms. That's different from the numbers on the periodic table. The molar mass, that's an average of all the isotopes for an element, right? So if you scoop some solid onto a balance in the laboratory and you get a weight, all those molecules add up to some mass and they contain all the isotopes, right? So carbon, is the most common isotope of carbon is carbon-12, but there's also carbon-13. And you know about radioactive carbon-14, carbon dating, like looking at fossils and seeing how old they are. Carbon-14, yeah, that's carbon that has 2 more neutrons than most of the carbon on planet Earth. Carbon-12, the most common form, and 2 more neutrons makes it carbon-14 and radioactive. So in a mass spectrometer, you can actually see individual carbon atoms, measure them, and decide if they're carbon-12 or they're carbon-13 or the rare form carbon-14. Okay, so those are 2 important points. One electron being removed, measure the mass, and we're looking at individual isotopes. Isotopic masses are measured in mass spectrometry. Okay, so a little bit, let's go into that in a little bit more detail. So on the internet, great place, find some data. I found this mass spectrum of bromine. Let's set the screen up so I got more room to draw and write. Put my picture over there. Okay, so this is Br2. Let's draw the Lewis dot structure of it. It's a covalent bond between two bromine atoms, and there's 3 lone pairs on each bromine. Right, you've seen the Lewis structure of Br2. Awesome. Well, why, this is one molecule. We can go to the periodic table. Where did I hide it? Right here. And we can look up the atomic mass of bromine. It's right over here, element 35. It's 79.904. Okay, so if you go weigh out some liquid bromine, that's the number you want to use to calculate the molar mass of Br2. But if you're measuring the mass in a mass spectrometer, well, you're not getting one peak, one value for the mass, you're getting 3. What's going on here? Well, you can go to another resource. I just use Wikipedia to list all the different possible isotopes for bromine. So isotopes of bromine are right here. Here are the different types. Over here on the right, it says the most stable forms. The most stable form of bromine is mass 79. There's also mass 81, and they're in nearly equal amounts. 51% of the bromine on planet Earth is bromine 79. 49% is bromine 81. But there's some radioactive isotopes also, right? So there's all the forms here from bromine 68 up to bromine, 97. And these are bromine atoms. What makes it bromine? It has 35 protons. That's the second column here, I believe. Double check. Yeah, the Z value is a proton number. They all have 35. And then how many neutrons, N? Well, they all differ in the number of neutrons. And depending on the ratio, or sorry, not ratio, depending on the numbers of protons and neutrons, it determines whether the element is stable or not. And it turns out for bromine, 79 and 81 are the magic numbers. So let's see, 79 is right here. So 44 neutrons makes a stable bromine atom, and 46. Can I click down there? No. It doesn't matter. There are 2 isotopes of bromine that are very stable. And that's actually what we're seeing in our data. Okay, so the Br2 molecule, well, sometimes you have both bromine atoms are mass 79. Add those together, that should be 158. And right here, you go to, so this arrow saying the first line right here, this value is 158 mass units. That's because both bromines have mass 79. The farthest one to the right is when both bromines have mass 81, that's 162. 81 plus 81 is 162. And then sometimes one bromine's 79, the other bromine's 81. They just have different numbers of neutrons. Cool. So yeah, we're measuring individual molecules, right? If you go to the periodic table, the atomic mass number is 79.9. That rounds off to 80. Why is it rounding off to 80? 80 mass units, 80 AMU? Well, because there's 2 isotopes of bromine, mass 79 and 80, and there's about, what did it say, 51% of 79 and 49% of the 81. There's about 50-50, half and half, a little bit more this side, so that's why it's not exactly 80, it's a little less than 80. This is the average of the isotopes. But the mass spectrometer is not measuring averages. It's actually saying counting individual bromine molecules. And sometimes when a bromine molecule shows up, it has both the 79 isotopes and weighs 158. Sometimes it has one of each, weighs 160. Sometimes it has the two heavier isotopes, it weighs 162. And sometimes it falls apart. Okay, so how do we measure the mass? We had to throw it into the mass spectrometer as a gas, and then we had to ionize it, right? It needs charge so it can navigate this magnetic field. If it's neutral, it just collides with the side of the magnet and doesn't make it to the detector. It has to have charge. And let's say we bombarded bromine with electrons. And so, yeah, where's my pen? So maybe we knocked out this electron. So this is the stable neutral molecule, the low stat structure for Br2. Put it in the mass spectrometer, ionize it by knocking out an electron. So one electron comes in and knocks out this one, two electrons leave. Does that make sense? One electron comes in, knocks out another electron, they're both out of there. And so now, this one bromine molecule looks like this. And this is unpaired. That's the definition of a radical. You remember when we were doing chlorination or halogenation of alkanes? Maybe we would take Br2, hit it with heat or light, H nu for light, delta for heat, and you could halogenate it, do a substitution reaction. Yeah, you remember that old reaction. And then the mechanism was initiation, propagation, termination. In the initiation step, we said the heat or light would break this covalent bond and make two radicals, bromine with a dot. Okay, that's what we got down here. These are radicals. Radicals are molecules or atoms containing unpaired electrons. But what else? When we knocked out an electron, originally, let's see, each bromine is element 35, right? Periodic table, please. There it is. Yep, element 35 is bromine. So a neutral bromine atom has 35 protons and 35 electrons. So in the Br2 molecule, there's 70 of each. But if you knock out an electron, you still have the 70 protons, but now you only have 69 electrons. You have a net +1 charge. It's a cation, or it's an ion, at the same time that it's a radical. Don't care so much about it being a radical because it's a charge that helps navigate the magnetic field. That's why there's a little plus charge on all of these, because technically that's what we're weighing, the mass of the cation. The problem is that just like Br2 with heat or light can split, this radical can help destabilize this molecule, and maybe this splits. Nature says, yeah, let's not do this anymore. I don't like my molecule being both a cation and a radical at the same time. So let's split this. And if I split this correctly, then this bromine on the left becomes Br. It still has its 3 lone pairs, becomes a radical. And the other one, well, it has 2 lone pairs, had the radical up on top, and then when the covalent bond split, you gain another radical. And so if you count up the electrons here, or maybe what you can do is just ask, hey, bromine, why don't you pair those up? And that can happen. It can be a diradical, or it could just have no radical character to it. It could actually pair up these electrons. And then it's missing a lone pair. This is a cation. This is also a cation. The main point here is that's what's very common in the mass spectrometer. We have to make them charged so we can analyze them, but the fact doing that makes them unstable. and sometimes they split. The molecular ion, which is both a cation and a radical, can become more stable by splitting into two pieces, one of which will be a radical, and the other piece will be a cation. And so we kind of got those two pieces, radical and cation, on separate molecules, and that's more stable than putting them both features on the same molecule. And then you can see here, hey, we got the bromine 79 to 81. We can measure, we can't measure this one. When it's a radical, it's neutral, no charge, so we don't measure that one. But the other piece, the cation, a single bromine atom, can be measured, and that's what we see. Sometimes the piece that comes off with the plus charge is 79 bromine, and other times it's 81. Hey, let's zoom in at the baseline here. You see two more pieces of data. Yeah, so there's two possibilities here. It could be that there's a little acid contaminating our sample, and a molecule of HBr that's a cation's making its way through. I don't know if that's true. That's a possibility though. What's more likely is that there's a low radioactive bromine 80 in here. That's mass 80. And there's a little bit of radioactive bromine 82 that's giving us this tiny peak right there. Anyways, thought that was interesting. Main takeaway, radicals, cations, and fragmentation. Molecules fall apart during the mass spectrometer analysis. Okay, back to the idea of we're measuring isotopes, not averages. So using a very powerful spectrometer that's finely tuned, high resolution, you know about HD TVs, high resolution television sets. Well, we got high resolution mass spectrometers. And that's where we can measure the mass very, very precisely, lots of significant figures. And we're not looking at averages, right? We're actually counting individual molecules with individual isotopes. And that actually provides another set of data here. So as an example to illustrate the usefulness of high resolution mass spectrometers, take for example C5H12, C4H8O, to two significant figures, they have the same molar mass. It's equal to 72 grams per mole. So using the averages, that's what we get. Average isotopic masses over here. Sorry, average atomic masses. I don't know why I circled sodium. There's no sodium here. But using the periodic table, you calculate the molar mass. You know how to do that. And the two sig figs, both chemical formulas are 72. So if we go in the lab and we have this unknown compound that somehow, maybe through colligative properties, do you remember that from general chemistry? You can use the freezing point depression or the boiling point elevation or osmosis. That data you can use to get the molar mass, the average mass of molecules. Suppose you had an unknown compound and you did an experiment involving osmosis, and you said, hey, my unknown compound has a mass of 72 grams per mole. What is it? Well, you're gonna need a lot more data than that, but you kind of narrow it down. Maybe it's one of these two molecules. Okay, not so useful because these molecules are not individual molecules. There's lots of isomers, lots of different ways you connect these together. But you can get more data if you analyze the same unknown compound, not through osmosis or boiling point elevation to get the molar mass, put it in a mass spectrometer, and more importantly, a high resolution mass spectrometer. Okay. And then what we see is, hey, a mass spectrometer can measure down to 0.0005 AMU, and this information may be outdated. Maybe there's better spectrometers and can get even more significant figures, more precision. But even with this precision, this is awesome. Using exact masses, meaning, hey, for C5H12, what's most likely is that all 5 carbons will be of the most common isotope of carbon, carbon 12. And the hydrogen, the most common form is H1. Just for laughs, I put up here hydrogen, the second isotope of hydrogen, H2. It's also known as deuterium. Here's its exact mass. It has one more neutron than the normal hydrogen with no neutrons, right? So the mass is doubled. But the 6 significant figures, we know its mass of an individual deuterium atom, individual hydrogen atom. Cool. But on average, most of the time, these molecules are going to have the most common isotopes. So all 12 hydrogen atoms will probably have mass of 1. And now if you use exact masses, carbon 12, actually this is what we set the AMU, atomic mass units, to. We say, hey, let's have carbon 12 be exactly 12 and get all our other measurements based on carbon 12's mass. So carbon 12 is exactly 12. We have 5 of those. We're just going to add up the molar mass here. But for an individual molecule, there's 12 hydrogens, and the hydrogen mass is this value. And now you get 72.0939. For the other formula, C4H8O, again, isotopic masses, use the exact mass for C12, H1, and then oxygen, the most common isotope is oxygen 16, and that has an exact mass of 15.99491. 491, yep. Add those up, and it's 72.05. So at the second decimal place, we got a difference between 9 and 5. That's so much bigger than this number. It's so easy for a high resolution mass spectrometer to see the difference between these two, that it'll then narrow this down. So if your data is, you go down, analyze your unknown compound that you formerly knew as 72 grams per mole, put it in the mass spectrometer, and it comes up with this value, well, it has to have this formula and not this one. Cool. So high-res mass spectrometers can actually identify molecules or help you identify a molecule. Okay, next page. Okay, more about radicals and cations and falling apart. Okay, so we mentioned before that the molecule has to have charge. By not getting an electron out, it's both a radical and a cation. Nature says, why don't we split those two instabilities, radical, cation, put them on different molecules. That's better. And you know what? Sometimes the cation then will do a carbocation rearrangement. Sometimes it'll split again, so forth. And so it turns out that during the analysis, the molecule can fall apart. Well, sometimes it doesn't fall apart at all. And that's when you get the molecular ions. The whole molecule is intact. Other times it falls apart. But if you have a big molecule and there's lots of pieces, you might see lots of pieces. And just remember, the radical has no charge, so it's not going to be detected. So we're only detecting the cation piece. But what's kind of cool is that every molecule has its own pattern for how it wants to split apart. And so the fragmentation pattern, all these little extra peaks, acts like a fingerprint, excuse me. And then if we just collect a whole bunch of mass spectra, a whole bunch of fingerprints for individual molecules, then when we have an unknown, we can measure its mass spectrum, a fingerprint, and match it up against a database or library of other mass spectra and identify our molecules that way. So very, very powerful instrument used in forensics all the time, as well as in scientific laboratories for identifying molecules. Cool. Okay, so let's get into the nitty gritty. Let's you and I figure out how to figure out or analyze this data. So a couple of key ideas. First of all, on the y-axis, we're counting, right? So the instrument is telling us how many times a molecule or a cation really comes by with a certain mass. And the base peak is the most common fragment or molecule that comes through. And so it's set to 100%, just arbitrarily. Find your biggest peak. The instrument will put that at 100%. And it turns out to be, that's your biggest peak. And we call it the base peak. We usually don't even look at the base peak. It's just there, base peak. If someone asks you, find the base peak, well, it's the biggest peak. Done. More important to us, though, is the molecular ion peak. Okay, so that is the intact molecule with one electron missing. It's both a radical and a cation, and it survived the trip to the very end, and we measured it. So here the molecular ion peak has a mass of 84. Turns out this is the molecule cyclohexane. Well, let's pretend we didn't know that. And all we did was we said, okay, here's an NMR, here's the mass spectrum data. And then because I had some experience analyzing this, I'll show you in a minute. This is our molecular ion. So I haven't told you how to find it, but there you go. This is our molecular ion. It weighs 84 mass units. And this is organic chemistry, so all our molecules contain carbon. So let's figure out a chemical formula for this with some C's in it. Okay, this is an individual molecule, so we're going to use the isotopic mass. We're going to say, hey, the most common isotope for carbon is carbon-12. So how many carbon-12 atoms, how many carbon-12 atoms can fit inside a molecule that weighs 84 mass units? Well, we're going to have to divide 84 by 12. Is that 7? 7 times 2 is 14. Carry 1 is 84. Yeah, it is. So 7 carbons can fit in there. Exactly. That's it. Wait, I thought the molecule was cyclohexane. Well, don't look at the answer. Based on the 84 mass units, the greatest number of carbon atoms that can fit in the molecule is 7. And then there's no more mass units, 84, for any hydrogen. That doesn't make sense. Most of our carbon molecules have hydrogen. I think all of them that we studied have. Okay, so what do? Well, the molecule still weighs 84 mass units. So what we have to do is take away a carbon atom so that we can put in some hydrogen. We still need the molecule to add up to 84 mass units. So if we take away 1 carbon-12, then we can add in some hydrogen. Well, how many hydrogens does it take that equal the mass of carbon-12? It takes 12 of them, right? 12 times 1 is 12. So divide by 12, find out the total number of carbons. And then when you don't like your formula, because I hate this one, there's no hydrogens, take away a carbon, leaving you with 6 carbons, so that you can add in some more hydrogens, 12 of them. Ooh, what's the chemical formula for cyclohexane? Well, here it is. If you draw out the condensed formula, there's 6 carbons, each with 2 hydrogens. That's C6H12. Beautiful. So we're going to be doing some math in here. And sorry, in my class, I don't allow calculators, but that's okay, right? We're college students. All you have to do is remember how to divide by 12 and do some adding and subtracting. Show your work. So if you make a math mistake, I'll take off a point for the math error, and then I'll pretend that the number you get is correct, and I'll see what you can do with it, and I'll give you more partial credit. And if things go sideways, like this doesn't make sense, go back and check your math. All right, what about those pieces, right? The radical and the cat, I got over here on the left side talking about molecules falling apart. Yeah, let's fall apart here. All these other peaks are the fragmentation peaks. So peaks lighter, less mass than the parent. All their pieces of the parent, the pieces of the original molecule, they're fragmentation peaks. That's what all these are. Wait a minute, we got this mass of 84. What's this mass over here? How can you have something bigger than the original molecule? Well, these are isotopic peaks, or just isotope peaks. The biggest molecular ion has the most common isotopes. So it's C6H12 in this molecule. And to get mass 84, that's where every one of those 12 hydrogens has no proton in it. Sorry, has no neutron. No neutron in it. It weighs 1 mass unit. And every single one of the carbons is carbon-12. But that's not always true, right? So in the real world, about 99% of carbon is carbon-12, and there's about 1% carbon-13. For hydrogen, 99%, it's about the same amount. Most of the hydrogen, 99% of it, weighs 1. About 1% of our hydrogen is deuterium, which is H2, has a neutron in it. Oxygen, nitrogen, phosphorus, sulfur, they're about the same. The most common isotope is a large percentage. Okay, so where this more heavy, smaller peak come from? Remember, the vertical axis means how abundant is it? How often did the instrument count a molecule of mass 85? Well, every once in a while. Out of the 12 hydrogens, maybe 11 of them are the most common form, but there might be a deuterium atom, a hydrogen with extra neutron in it. Or maybe there's 5 carbon-12s and there's a carbon-13 in there for 6 total. So I know that's a weird looking chemical formula, but the idea is that among the atoms of carbon and hydrogen, every once in a while you get one with extra neutron in it, a C13 or a deuterium atom, and that's going to weigh 1 more mass unit because of the extra neutron. It's going to weigh 85 mass units. Some of you might be saying, well, isn't it possible to have a molecule with both a C13 and a deuterium atom in it? And yes, it is possible. But that's only going to happen 1% times 1% of the time. 0.001%? No, sorry. Let's go decimal. Should have did the math before. Multiply that together. That gives you that. Change it to the decimal. Okay, so that's only going to happen 0.01% of the time. Not very often. So if you zoom in, you might be able to detect a mass at 86 for the times when both a C13 and a deuterium atom show up in the same molecule. Okay. Now, among the fragmentation peaks, you can also have isotope peaks mixed in there. So what are we talking about here? Okay, so start with the original molecule of mass 84. That's cyclohexane. And how'd you get mass 56? Well, the most common cation that's making through the mass spectrometer has 56 mass units. Let's assume it's the most common forms, C12 and H1. So divided by 12. So is that 4? 4 times 12 is 48. Yeah, that's going to work. And then subtract 8 from that. So 4, carry a 1. What was it called in the new math? It's like regroup. Regroup that. 16 minus 8 is 8. So the formula for mass 56 could be 4 carbons and 8 hydrogens. So what's left over is the number of hydrogens. And then I should probably check my math. C4H8, let's see, that's 4 times 12, which is 48, plus 8 hydrogens, that weighs 8, 48 and 8, yeah, that's 56. Good. Check my math, that looks good. C4H8, if it came from cyclohexane, it's like a butane fragment. It's 4 of these carbons, like this piece right here has a cation. Probably not primary, it's probably rearranged. So this mass 56 is probably this cation. It lost 2 carbons and the associated hydrogens. Well, where'd they go? Well, 2 carbons with hydrogens, make it a cation here. That's C2H5. So I did the math earlier. 2 times 12 is 24, plus 5 is 29. Yeah, so here's the other piece. Sometimes when cyclohexane flies through the spectrometer, it splits twice, breaks 2 bonds. So you get a little ethyl cation showing up with mass 29. Most of the time, though, it's the 4 carbon group, this butyl cation, makes it through with mass 56. But you know what? Maybe on here, one of these hydrogens is a deuterium atom. And that's going to give us 1 more mass unit, 57. So just illustrating here that among all these peaks, most of the peaks that are smaller than the molecular ion peak, definitely, they're fragmentation peaks. But also among them, like this mass 57, it's also a mixture of fragmentation and isotopic. There's an isotope in here, one of the rare isotopes, deuterium, that's showing up in a fragmentation peak. However, once you're confident you identified the molecular ion peak, anything heavier than that, those are always isotopic peaks. That's the only way to make something bigger, is if the heavier isotopes are present. Okay, I think we got everything done here in terms of analyzing and naming different types of peaks. Oh yeah, mass spectra like fingerprints. So this is a much better spectrum. You can see how there's groupings of peaks. Each peak has different heights. And so we might have another molecule that's C6H12. What's another molecule? Well, how about we have cyclopentane with a methyl branch? That's C6H12. If you look at the mass spectrum of that, you're going to get a molecular ion peak of 84. It's going to fall apart differently though, right? There's a tertiary carbon here that might be more stable than the secondary carbocation. The base peak is probably different because the carbocation here is tertiary. That might be more stable. And this is not going to have mass 56. So already, if you analyze the mass spectrum of this, we should see a different base peak. We're going to get a different looking mass spectrum. It's going to be a fingerprint for this molecule. They'll be different from the fingerprint, all these peaks, these heights, this distribution of peaks, different fingerprint for cyclohexane. Cool. All right, that everything on this side? All right, more nitty gritty. Let's go into full analysis mode. So let's put us in the realm of what do we do on an exam? What do we do for the homework? Well, 3 steps when dealing with the mass spectrum. First, key and foremost is very carefully double check your work. Find that parent peak. It's not always obvious, and sometimes we make mistakes, but as we start doing analysis, maybe we'll find an error. It's like, wait, this doesn't make sense. Find that parent peak. From the parent peak, do a little math and calculate some possible chemical formulas. So you're going to divide by 12. The leftovers are hydrogen. What about the other elements? More on that in a minute, but here's the strategy. Find a parent peak, divide it by 12, get some possible chemical formulas. And then once you have a chemical formula, calculate your degrees of unsaturation. How many pi bonds, how many rings are in the molecule? That'll allow you to draw some possible structures. There you go. So very quickly you can get to some possible answers for your unknown compound. All right, more details on those things. Here's the guideline. Step 1, find the parent peak. Well, to find the parent peak, find the cluster of peaks farthest to the right. So I marked up all of this one. Well, this one's not too bad. So if you look at the overall, just kind of step back, look at the forest from the trees. You got some peaks here, 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 and here. These are clusters, right? 1, 2, 3, 4, 5, 6 clusters of peaks. Go to the cluster of peaks farthest to the right. And then within the cluster of peaks farthest to the right, go as far to the right within these peaks and pick your largest one. That's usually the parent peak, the molecular ion peak. I know, do that again. That's right, so find the cluster of peaks farthest to the right. Within this rightmost cluster of peaks, the parent peak is, well, I should say usually the tallest peak to the right. And then once you have that parent peak, get its value. How massive is it? What's the mass number? Actually, the mass to charge ratio, but charge is assumed to be 1, so find the mass. Divide by 12, find the maximum number of carbons. The remainder equals the number of hydrogens. Okay, to find additional chemical formulas, remember how we did that with the cyclohexane? It had mass 84. We divide by 12 to get 7. and our chemical formula is C7. Ew, that's not a real organic molecule. You had to subtract 12 for carbon 12 so that we could add in 12 hydrogens, and we got a new formula. And guess what? If we had some other analysis that said this doesn't look good, you can do it again. So subtract the C12 and add in 12 hydrogens, whoops, 12 H1s. And your new formula would be C5H24. Ooh, if you count the degrees of unsaturation, it's not going to work. This is super saturated. 2 times 5 plus 2 more is the maximum number of hydrogens that 5 carbons can hold, and that's equal to 12. 2 times 5 plus 2 is 12. So this is a wrong formula. Okay, but you see the pattern, right? If you want additional chemical formulas, take away carbon, add in some hydrogens. Do the same thing with other elements. So let's say you have some data, or you suspect maybe there's oxygen in here. Well, we have the chemical formula C6H12 has a mass of 84. So you want to add an oxygen. How much does oxygen weigh? Well, let's go to the periodic table. Is it over here somewhere? Maybe down here. Maybe. Where's the periodic table? There it is. Oxygen, where are you? You're over here on the upper right. The atomic mass unit, the average of all the isotopes is 15.9994. Okay, the average is closest to the most common isotope. And isotopes are always whole numbers because they have protons and neutrons in them, right? Whole numbers of protons, whole numbers of neutrons, can't have a fraction of a neutron. Anyways, 15.99 is closest to 16, and that's the most common isotope of oxygen. Do that with any elements. That's how you get the most common isotope. Okay, so let's get another chemical formula of C6H12, but this time we want an oxygen in it. So the most common isotope is oxygen 16. One oxygen atom is going to weigh 16 mass units. So out of the 84 mass units of the whole molecule, I want 16 of those to be from oxygen. So I want to add in an oxygen that weighs 16. That means I have to take away enough atoms that add up to 16. Well, let's start with a carbon, because that's 12 mass units. How many hydrogens will add up to 16? 4 of them. So, right, 4 hydrogens weigh 4 mass units. Carbon 12 weighs 12. 12 and 4 is 16. So if I take away a carbon, so it says C6, I have C5. Take away 4 H's, so not 12, but 8. Then I can add in an oxygen. And you know what? You might want to just check our math. Is 5 times 12, right? 5 carbons plus 8 hydrogens, because each hydrogen weighs 1, and plus the 1 oxygen, 16. Well, let's see, 5 times 12 is 60, plus 8 is 68, plus 16, 8 and 6 is 4, carry a 1. That's, ooh, yay, that's 84. And that's how much the mass data, the molecular ion peak said. So yay, this works. There's a new chemical formula. And if you want a second oxygen, do the same thing. Add another oxygen and take away another carbon, 4 hydrogens. Ooh, that's only gonna leave you with 4 H's. That may not be a real molecule. It's possible to draw one, so maybe it is. If you want nitrogen in there, do the same thing. You want some halides, same thing. Add in a halide, take away enough atoms so that the total mass still matches your molecular ion peak. All right, let's try that. So, what's this molecule? I don't know. Let's try and find some possible structures for it. Now, one piece of data, one mass spectrum, unless you have access to a mass spectrum library, you're not going to be able to identify it. Even if you had the library, you still need more data to conclusively identify a molecule. So with one piece of data, mass spectrum, we're just going to get some possibilities. We're going to narrow down the number of possibilities. Right now, it's unknown, don't have any idea, but with the mass spectrum, we can actually narrow it down. Step one is find the molecular, find the parent peak of the molecular ion peak. So where is it? Go to your rightmost cluster. So I see a cluster of peaks here, 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 and right here, nothing beyond that. So the rightmost peak is right here, and find your biggest peak. So I suspect it's this one. Biggest peak farthest to the right. Okay, now let's check our answer. Check our answer by thinking about what we know about mass spectra data. And that is there's two types. There's fragmentation, there's isotopic. So it's too bad you can't get the whole thing on screen. So does it make sense that if this peak, it's not gonna work. Let's go back to small. So does it make sense that this is our molecular ion peak? That would say that this peak right here must be an isotope. And yeah, that does make sense because isotopes are gonna be small, right? Because most of the isotopes are rare, right? Carbon-13 was 99%, C12, only 1% is C13. Same is true with H1, about 99%, only 1% is actually a heavier isotope. So less often we'll see the isotope peaks. Yeah, it should be small. This does make sense. What about this peak? That's a pretty big peak. Why is that such a big peak? Well, it turns out this is a fragmentation peak, right? Things are less massive, smaller values must have been pieces of the original molecule. And this is one mass unit smaller. Well, what's one mass unit? A hydrogen. So it looks like this molecule likes to release an H. As it's flying through the mass spectrometer, that radical cation kicks out probably an H radical. So the rest of the molecule is a cation with one missing hydrogen, so it has one missing mass unit. Okay, so this one right here is the molecular ion peak. It's the molecule M, that's both a cation and a radical, the intact molecule. Okay, let's zoom in now, because now I need to carefully measure the mass number. What is the weight of that peak right here? Not this one or that one. What is this? So just go down here, and it's kind of nice because it got all the little tick marks. It's this one here, right? That's the mass we want. Okay, so where are we? Well, it looks like, let's go over here where it's not marked up. I got 75, and that looks like 80, 85, 90, 95, 100. Good. This is 105, this is 110, this is 115. Then this one right here is 120. And so if this is 115, this is 116, 117, 118. And yes, you do have to zoom in and be real careful, right? If you get the wrong number, you may get the wrong chemical formula. Cool, mass is 118. Step one's done, we found the parent peak. What do we do with that number? Oh, don't zoom in on it, give me some more room. You divide it by 12. Let's go after a chemical formula. All right, and again, we're college students. We know how to divide by 12. Is this, well, if it was 10, that'd be 120. That's 118. So it's not 10 carbons. Maybe it's 9. 9 times 2 is 18. Carry 1. 9 times 1, it's 9 plus 1 is 108. Or remember your times tables. 9 times 12 is 108. Subtract that. Little long division here, and that's 10. Okay, the leftovers are the hydrogens. The number of times 12 goes in the molecules, the number of carbons. There's a formula, C9H12. Awesome. If you don't like that, subtract the carbon and add in 12 H's. So that'd be C8, H2. Ew, I don't like that. That's too few. Probably not. Okay, so why not? It is possible to draw a molecule that has 8 carbons and 2 hydrogens. Lots of degrees on saturation, lots of rings, lots of pi bonds, whatever. But this is real data. So where'd you get this real data? Well, from real molecules that exist. Things are stable and cheap and easy to find. So this is going to be a very unstable molecule with a lot of rings, a lot of pi bonds. It's going to be expensive, or maybe it just doesn't exist. No one's made it yet. It's going to be pretty rare. It's not going to be something I can go find and give to you as a homework or an exam question. These are going to be common molecules or very stable molecules. So when you start seeing chemical formulas that are weird, like only a few hydrogens, be suspicious. Like, I probably won't spend my time thinking about molecules with this weird chemical formula. This one looks more realistic. Okay, let's count degrees. That's step 2. Once we have a chemical formula, remember the math. Got to do a little multiplying and adding. Okay, so what's the formula? The number of saturated hydrogens is 2 times the number of carbons plus 2 more. So if the molecule is saturated, it should have 2 times 9 plus 2 more hydrogens. And then we subtract the actual number, 10. And there's no other elements present, so that's our numerator for the equation. Divide the whole thing by 2. And then 2 times 9 is 18, plus 2 is 20, minus 10 over 2. Well, 20 minus 10 is 10, divided by 2. Hey, that's 5. 5 degrees. Technically, that means 5 rings, or 5 pi bonds, or 4 rings and 1 pi bond, or 4 pi bonds, 1 ring, or 3 pi bonds, 2 rings. You know, it's all a combination of rings and pi bonds. However, nature has some favorites, right? She really likes the arene functional group. It's one of her favorites. So it's not a guarantee, but again, this is real molecules, real data, common molecules. It's likely to have a benzene ring in it because benzene has 1 ring and 3 pi bonds for 4 degrees. So anytime you calculate the degrees of unsaturation and you get a number that's 4 or greater, suspect benzene. That'll probably lead you to the right answer more frequently. It's not a guarantee though. It may not have a benzene ring. Just be a little cautious. So that's my suspicions. I suspect a benzene ring, where the shortcut for benzene, that's going to carry 4 degrees, 1 ring, 3 pi bonds, and then there's going to be another ring or another pi bond to add up to 5. And using that, we can start drawing structures. Cool. So here's some possibilities. We need more data to figure out which one's the correct one. We don't have more data at this point, so we're just going to put down some possibilities. So possible structures, C9H10, and I suspect the benzene ring, so let's start with that. That used up 6 carbons. There's 9 altogether, so one possibility is the 3 of them are over in the chain. Oh yeah, but I still have 1 more ring or a pi bond, so let's put a pi bond here, or maybe you could have put it here. Can I put it here? No, that would give this carbon 5 bonds. But this is trans, maybe we could have the cis. If you want to draw that, that's a possibility. Doesn't have to be a pi bond. What if we have another ring? 1, 2, 3 carbons, 6 in a ring. Yeah, this has 5 degrees of unsaturation. It should be C9H10. Another possibility is maybe there's 2 carbons here with the pi bond, and there's another methyl group, and so forth. So already we have 4 possibilities. And if this is an exam question, you get full credit. Now, the question would be more specific. It might say draw at least 3 structures, 3 possible structures. It might say just 1. There you go. Yay. Now we need more data to figure out which of these 4, maybe there's something else I haven't drawn, is the actual molecule that produced this mass spectrum. If I don't have that data today, that's in future videos. All right, let's analyze another one. Same idea, find the parent peak, calculate some possible, calculate degrees of unsaturation. Sorry, no, calculate some possible formulas, then the degrees so you can draw. All right, so new mass spectrum. All right, so step one, find the parent peak. Find your clusters. Here's a cluster, there's a cluster, here's a cluster, farthest to the right. Find the biggest peak. Here it is. That's my parent peak. Or is it? Okay, so that's the process. Now you need to check. If this is the parent peak, and there's the standard way of identifying it with symbols, molecular ion peak, that's both a cation and a radical. What is this then? Well, if I say this has to be the molecular ion peak, then this has to be an isotope peak. It's the only way to make it bigger. But look how tall this peak is. Look how common it's showing up. The base peak happens to be the parent peak, right? Base peak's the biggest peak. So most of the time this peak shows up in the mass spectrometer. This peak's also showing up a lot too. The isotope peaks are rare, right? Only 1% is C13, only 1% deuterium. Those should be little peaks. Okay, so here the little guideline, the largest peak in the rightmost cluster should be your parent. It didn't work out because this one's too big. So maybe this one's the molecular ion peak. Does that make sense? Well, anything bigger? Yeah, there's only this one, and it's tiny. That's how isotopes should be. The isotope peaks should be small because they're rare, only 1% of the time for carbon-13, so forth. Then this big peak, does that make sense? Yeah, it kind of does. Whatever this molecule is, as it's flying through the spectrometer, it likes to kick out a hydrogen. This is a fragmentation peak. Oh, frag peak. This makes the most sense to call this one the parent peak, not the biggest peak. Sorry about that. I know it's nice to have nice guidelines, but these are not rules. Largest peak, farthest right, is possibly the parent peak, but look left and right of it, see if it makes sense. It makes the most sense calling this one the second largest peak the parent, because next set of peaks bigger are tiny, and then who cares about the other ones? Sure, this large one could be fragmentation. If it was small again, I could still say, well, molecule does not like kicking out a hydrogen, but it happens every once in a while. That's why it's smaller. Okay, that's probably the hardest thing. And if you show your work, like if I see, if I'm grading this, you X this out and you said that's a fragmentation peak, I'd say, I like your reasoning. Let's just go with that. And if it turns out not to be correct, at least I can give you partial credit for showing me that. Okay, step one is almost done. We found the parent peak, but now we need the mass value. So let's go down here. I like to zoom in. Can I get both on the screen at once? I don't think I can. That's too bad. Oh yeah, I can. Cool. Let's get this out of the way. All right, so this peak right here, it's right there. So what are these numbers? Wait, the last spectrum labeled every peak with a number, and this one doesn't. Dennis, how are you gonna do this? Okay, what you need to do is scroll over here till you see something with a lot of peaks. And kind of get familiar with the spacing between the peaks. So over here, this one's nice because I got a little tick mark here and a tick mark here, tick mark there. What are these numbers? Well, we're told this tick mark is 40, this one's 60. And so it makes sense that this is 45, 50, 55, 60. Cool. And then if you find a cluster where there's a lot of peaks, you can see that, hey, this one's 50, this one's 51, 52, 53, and that one's 54, and then here's 55. And what are we doing? We're getting familiar, we're getting a little comfortable with the spacing. This distance is one mass unit. And we kind of confirmed that, right? So we found a peak here, 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 and here. There's a tick mark. They're all evenly spaced. We're all one mass unit apart, and I proved it. 50, 51, 52, 53, 54, 55, proved it. So now I can just look at this and say, these are one mass unit apart. These are not, right? That makes more sense. This, that here is one mass unit, that there's one mass unit, because that's what this data told me. Okay, Now let's go look at that parent peak armed with this data. Ooh, I can keep it on the screen too. Okay, so this one I got labeled as parent, which is right here. So this distance to there is 1 mass unit. This distance to there is not. That looks like 2 mass units. I think there's a little tick mark right here. So let's check and see. Maybe we'll go over here a little more accurately. This is 100. So this number should be 105. And this one is 110 because this one's 115 and this one's 120. Good. And then this is 1 mass unit. So this is 106 and this is 107. Yay. And so I like seeing this on your work and give you partial credit. If I see that you said it was actually 109, I would have said, oops. Yeah, this is the 110 mark, but this is not 109. Yikes. Anyways, hope I made that clear. So over here, one mass unit is this far apart. Count them up. Yeah, 107. That's the mass value for our parent peak. What do you do with that? You divide it by 12. So maybe I got a little room right here. 107 divided by 12. Ooh, before I get started on this, let's point out one more thing. This is an odd number. That's kind of odd. Turns out that most organic molecules have even numbers. It's weird. Carbon bonds 4 times. That's the main reason. But hydrogen has an odd number, H1. The halides, they have odd mass units. And it turns out most organic molecules are going to have an even number. So as soon as I got 107, I should have been a little more careful and realized, wait, let me go double check this, make sure it's really an odd number, because that's unusual. Odd number, you remember, before hashtag, this meant number. Okay. I'm pretty confident that we did this right, and the mass number is 107. So what that means is that we have an odd number of nitrogen atoms. So remember HONC, 1, 2, 3, 4. Nitrogen prefers 3 bonds. And oftentimes the nitrogen will bond to a hydrogen. It'll bring in an odd number of hydrogens, making for an odd molar mass. Okay, so that's a new clue for mass spectroscopy. If you actually are confident you are getting an odd number for your parent peak, then you have an odd number of nitrogen atoms. Now, this is supposed to be a real molecule, a common molecule. So what are some common values for odd numbers of nitrogen? Just 1. It is possible to have 3 nitrogens in the molecule, or 5, or 7. It's possible. It's just not very common. So we probably have 1 nitrogen atom. So before I do this dividing, let's take care of the nitrogen. The odd numbers telling me I probably have a nitrogen atom. So what's the mass of the most common isotope for nitrogen? Well, let's go to the periodic table, which you get on every exam. The atomic mass number for nitrogen is 14.0067. It's right here. And so round that off to 14, and that's the most common isotope, nitrogen 14. Nitrogen 14 weighs 14 mass units. So out of 107 total, 14 of the mass comes from the nitrogen atom. That's what I suspect because of the odd number. Regroup the 10 so I can carry out. Why am I doing that? Yes, even I make mistakes. Kind of wish I had the calculator here too. But we're not going to get one. We're college students or we're professors with PhDs. We ought to be able to subtract. 7 minus 4 is a 3. 10 minus 1 is a 9. Yes, we can do this. Okay, check your math. We're all good. Check my math. So 93 plus 14, 4 and 3 make 7, 1 and 9 make 10. Good, that's 107. Excellent. Now let's take the 93, because I subtracted out the weight of the nitrogen. Divide this by 12. 8 times 12 is 96. So that's too much. 7 times 12 is 84. This time we're going to regroup. 8 and 1. 13 minus 4 is 9. Check my math. 9 plus 4 is 13. Carry 1, 9. Yes. Okay, so this number is the number of carbons. This number is the number of hydrogens and nitrogen. We have our chemical formula. 9 and 7, that's going to be unsaturated. Think about other possibilities. Maybe I don't want to subtract the carbon and add in 12 more hydrogens. Probably not. 12 more H's would be 21. That's way too many for 6 carbons. So sorry, I'm talking out loud when this is a video. I show some stuff. I'm thinking about another formula where you take away the carbon, C6, add in hydrogens, that's 21, keep the nitrogen, but that's supersaturated. 6 carbons can only, 6 times 2 plus 2 more is 14. That's the maximum number of hydrogens, 14, if you have 6 carbons, and you can't have 21. This is not, this is not a possible chemical formula. That's bad. But at least we know how to calculate other formulas if we didn't like this one. We can also put in an oxygen here, but it'll take away 4 of our H's. Let's just do that off this side, because other problems, we might have to do that. So if we want to add an oxygen, we're going to subtract the carbon 12, 16, 16, and we have to subtract out 4 H's, a total of 16 mass units. So take away a carbon, that leaves us C6, take away 4 H's, that leaves us H5, ooh. And we have a nitrogen, now we get an oxygen. That's still possible. I don't like it though. Okay, let's go with this one. And if we had more data and the formulas, the structures that we get from this, if they didn't work out, then maybe we would have to go with this one. Okay, let's try this one. C7H9N. Let's calculate the degrees in saturation. Well, that's 2 times 7 plus 2 more, minus, well, it actually has 9 hydrogens. It also has a nitrogen. If it was a halide, right? Halides count like hydrogen. They both start with H's. So all the halides, chlorine, bromine, fluorine, we would pretend they're hydrogens and add them in, but not nitrogen. It's negative. That's how I remember it. So a nitrogen atom shows up, we need to subtract away 1 hydrogen for every nitrogen. Now we do the math. 2 times 7 is 14, plus 2 is 16. 9 minus 1 is 8. 16 minus 8 is 8. Divided by 2 equals 4. Red flag. I suspect benzene, because that's 4 degrees of unsaturation. But it doesn't have to, right? We could say, okay, so now that's the degrees. Got to have 4 degrees. So maybe there's 1, 2, 3, 4, 5, 6, 7 carbons and a nitrogen, and then I need 4 degrees. So how about we put a double bond here, here, and here, and I need 4 degrees, 4 pi bonds. I don't like putting pi bonds next to pi bonds because that's unstable. Nature doesn't like doing that. That's an alene type of structure, and we're trying to draw the most common molecules. So I would give you points if you draw it on the pi bond. That is an isomer of C7H9N, but I would say that's probably not it. So maybe make it a triple bond instead. That's more stable. And this has 4 degrees unsaturation. I would probably take off half a point because this is not a nice pure skeletal drawing, because it's okay to leave off your H's, but only when they're attached to carbon. This nitrogen only has 1 bond. It needs 3, which means you have to show the H's or attach some carbons. Okay, now that's a good drawing. And you know what? You can move this nitrogen around the ring, around the chain. So maybe put the nitrogen here. 1, 2, 3, 4, 5, 6, 7. Yeah, this still works. Or put the nitrogen in the chain. And maybe put some branches off of it. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Yeah, 6, 7. I need 4 degrees on saturation. There's a structure. That works. What if you like the benzene? Well, just stick on the nitrogen then. And there's 6 carbons, put on a methyl group. There we go, there's 7 carbons now. There should be 9 hydrogens. You can also put the carbon and the nitrogen together. Oh, you know what? Now think about functional groups. I got amines all over the place. What if there was a nitrile in the molecule, right? So you have a nitrogen carbon triple bond, that's a nitrile. And this is 1 out of 7 carbons, so I attach a second, third, fourth, fifth, sixth, seventh. So 1, 2, 3, 4, 5, 6, 7. Good, I got 2 degrees already, so put in 2 more, whatever I like. Okay, so there's some possible structures. Okay, I think there's one more. Let's do this one. Not that one, but we'll do that one too. Sorry, I meant to start with this one. But we're gonna do this one first. Yeah, I should do this first. Let's just do this one. Okay, step 1, find the parent peak. Go to the right, find your biggest peak. Does that make sense? Should this one be the parent? Is this the M plus dot? Well, I'm worried about this peak. Is that really an isotope peak? It's so common. It's so, yeah, that doesn't make sense. Or does it? Okay, we talked about odd numbers showing up in a formula. So that's something to look for. So odd numbers showing up in our mass spectrum. Suspect nitrogen if you have an odd number. The other thing is way back here when we first started talking about isotopes. We showed this one with Br2. And it turns out bromine is unusual. It has a very common isotope, right? So the most common isotope, 51%, is 79 bromine. But 49% of the time, very common, it's bromine 81. So if you ever see twins like this are separated by 2 mass units, 79 to 81, suspect bromine. So let's take a look at this. What's going on here? Well, these two, they're almost twin peaks here. Are they 2 mass units apart? I think they are. Let's see if I can zoom in. Yeah, we'll cut it off here. So this is nice. We're seeing individual tick marks. So this is 110. So this one's 105. Yeah, so every marking is 1 unit. So this is 106, 7, 8. This is 108. That's 109. And this one is 110. They're 2 mass units apart and they're twins, right? They're nearly the same height. So if you see twin peaks, nearly the same height, that indicates bromine. So they're twins, 2 mass units apart. That tells you have a bromine atom in your molecule. And guess what? If the molecule falls apart and keeps its bromine, you'll see more twins. So here's another twin, and here's another twin. Here's another twin right here. There's another twin up there. Ooh, that's not a twin. Well, actually, there's some overlapping peaks. I think the twins are in here, but there's also a fragmentation peak that's adding up here too. You don't have to have twins everywhere. Actually, that doesn't make any sense. What's the weight of bromine? 79. And 81. This one at 20 something, they can't have bromine. Silly me. So, okay, this is a good example where I see a pattern, tried to apply it, and then I checked it and it doesn't work. So keep in mind that, right, you find the parent peak, peak's larger, must be isotopes. Does that make sense? It does here. Usually isotopes are tiny, they're rare. But if you have the twins, one, this peak, inside that molecule, there's a bromine 79. And in this one, in this molecule, there's a bromine 81. And that makes sense for this isotope peak, it's an isotope peak, to be so big because bromine 81 is very common. Then what's this peak and this one? They're twins also. Well, this one has bromine 79 and a C13 or a deuterium atom. And then this one has the bromine 81 and a carbon 13 or a deuterium. Okay, it does make sense that these are isotope peaks. So I think we did it. The parent peak is 108. Cool. And we have a bromine. Okay, I don't like the resolution. It's all pixelated. Step one was find the mass number. It's 108. We got a bromine. Use the most common isotope. Periodic table, where'd you go? Go to the mass of bromine. It's 79.9. I guess this one you have to remember. You round it off to 80, you have the wrong value. It's 79 and 81. They twin that up to the average of 80. Actually 79.909, 904. So bromine you have to know. The isotopes are 79 and 81. So only take the first part, the 79, for bromine. And you know it's bromine because of the twin peaks. So take away 79 mass units. I do need to regroup this. So 18 minus 9 is 9. 9 minus 7 is 2. Check my math. 79 plus 29. 99 is 18. Carry a 1. 8 and 7 is 8. Let's do is 108. Good. That's what we have. Ooh, 29. That's not bad. Divide that by 12. It's only 2 times. 24. Subtract that is 5. So we have 2 carbons, 5 hydrogens, and 1 bromine. Wow. I think we know what the molecule is. It's ethyl bromide. Is there anything else? Nothing else we can draw. Hey, that's cool. That is the answer. Yeah, I can't think of another way. Bromine bonds 1 time. Yeah, beautiful. Didn't need the degrees of unsaturation. It was just such a small molecule, only 2 carbons. Let's do the last one here. We'll end the video with this one. Ew, go to the rightmost peaks, and it's a real mess here. But here's something else I want you to know. This I would suspect to be the parent. In the rightmost cluster, find the largest peak. Doesn't make sense. I'm worried about this one. That doesn't look too small. These do. These look like isotopes, right? Anything bigger than the parent, I'm going to pretend that's the parent. That's my suspicion. Anything bigger than the parent should be little peaks because they're isotope peaks, the rare forms of most of the elements. This one doesn't look so rare. But wait, it's 2 mass units apart. If it was a twin, it would have been bromine. This one is 1/3 as big as this one. Wait a minute. Is that happening somewhere else? Ooh, it happened here too. We got 2 mass units apart. This is about 1/3. Ooh, here it is again. This is about 1/3. Ooh, here it is again. This is about 1/3. I'm not really seeing it elsewhere. That's okay. You only need to see it a couple times. This is indicating that there's a chlorine atom. Chlorine has 2 isotopes, 35 and 37. But unlike bromine, there's 2 isotopes. They're nearly equal. Chlorine 35 is about 75% of the time, and chlorine 37, the heavier one's only 25% of the time. This happens about 1/3 as much as that, right? 75 divided by 3 is 25, 1/3. Yeah, so if there's a twin peaks, these might be fraternal twins, they're not identical twins, and they're 2 mass units apart, that indicates a chlorine atom. So yes, it makes sense that this isotope peak is so big because we got a chlorine atom here. All right, let's get a measurement of that value. So it's that big peak right there. So let's go find, ooh, here's a bunch of peaks all clustered together. So what's the width of one? Well, 40 to 80, this little tick mark must be 60. This one looks like 70, and then 70, 80. So is this 71, 72, 73, 74, 75? Okay, that's a big gap. 76 should be in the middle, then 78. That count right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 80. Good. All right, pause the video, count it yourself, make sure I did it right. This gap is 2 mass units apart. These individual peaks are separated by 1 mass unit, as are these. So from here to there, that looks like 1 mass unit. So what's this value? That's halfway between here, that's 140. So this is 141, and my parent peak is at 142, right? I'm saying that's the parent. This one is the M plus dot peak at 142. Oops, wrong way. Okay, so 142 with a chlorine. So take out the chlorine atom. Go to the periodic table. So one over here. Yes. What's the mass of chlorine? It's 35.45, so round it off to 35. 35 is the most common isotope for chlorine. All right, 2 minus 5, can't do that, regroup. So 12 minus 5 is 7, 13 minus 3 is 107. Hey, we just did this one. Sort of. Okay, so check my math. 5 plus 7 is 12, that's a 2, carry 1, 3, yeah, 142, excellent. All right, now 107 divided by 12 is that 9 is 108, 8 is 80, 96, let's check it, 96 I think. 9 times 2 is 16, carry 1, 8, 1 is 9, good. Subtract this as a 1 and a 1, really? Cool. C8, H11, Cl. Check my math, 8 carbons weigh 12, 8 times 2 is 16, 8 and 1 is 8 plus 1 more is 16, sorry, it's 9, why? Brain. 11 hydrogens, that's 7, 107, and the chlorine, 35, that's 12 again, carry a 1, that's a 41. Good, 142 is what we said the parent peak was. So this is a good chemical formula. Count up the degrees. Okay, there's 8 carbons, so 2 times 8 plus 2 more. Subtract, sorry. We actually have 11 hydrogens, and then the halide counts like hydrogen. So add in another hydrogen for the chlorine. Divide the whole thing by 2. 2 times 8 is 16, plus 2 is 18, minus 11 and 1 is 12. Divided by 2. 18 minus 12 is 6, divided by 2 is 3. So then I have, I have 3 rings, or 3 pi bonds, or we have 2 rings and a pi, or we have 2 pi and a ring. Anything else? We have 1 ring, 2 pi bonds. I already got that. All right, those are possibilities. I don't have a benzene ring because I don't have 4 degrees. So 8 carbons. Maybe I have, let's do this one just for, maybe I have a ring of 6, cyclohexane, and then that's 6 carbons. There's 8 altogether, so put 2 out here. That was my ring. So add in 2 pi bonds. Well, how about 1 here, 1 there, and then throw in a chlorine. I'll put 1 there. That's a possibility. Maybe you want to do straight chains. So 8 carbons in a row. 1, 2, 3, 4, 5, 6, 7, 8. You got 3 pi bonds maybe. So maybe I'll put a triple bond in there, put a chlorine at the end of the chain. Who knows? All right, so those are some possibilities. Cool. Let me check my notes, make sure I got everything. I think we're good. All righty, that's plenty for this video. I'll see you in the next one.